All right, everybody. So, what'd you think of the midterm? Not too bad, right? No? Okay. Does that mean not too bad, as in no, not too bad, or no, it was bad? You thought it was hard? Too long? Well, okay, but here's the problem. If I make it shorter, right? Then it's like, what if you don't know how to do one of the problems? If there's only two problems on it, is that really a good sample size? So, okay. So maybe we'll try three problems next time in multiple choice. Would that be a little better? Okay. Okay, go ahead. No, like three free response and four multiple choice. So maybe just like one problem less. Would that be better? Okay. All right. Well, we'll do that. We'll do that for the next one. And then in the meantime, if you're worried about it, just remember that your grade on the final, if you do better on the final, it replaces your grade on one of the midterms. So that's a chance for you to boost up your score as well. That, while it seems like a long and distant hope right now, I have seen that help out a lot of people. Okay, it's not a guarantee, obviously. It kind of depends on the situation. But in general, I've seen people go from maybe they got like a C or something on the first one. They get a final on the final. Maybe they get like a B or B plus, A minus even. That's two scores then that it counts for. And I like that because it sort of gives you the option of making the final worth a lot more, but it's not like going to crush you if something happens. Like if something happens where you don't do amazing on the final, it's not like the only thing you have, right? Yes. Right. Okay, well that's a good idea. So maybe there's things I like about that and there's things I don't like about it. I don't like it if it just becomes like it's a giveaway, like it's obvious which equation you need to use. I think that it's kind of important for you to be able to know when you can use one equation versus another. So I try not to give away too many hints. I think I did on one of the problems do make that suggestion, didn't I? One of the problems did have that. Okay, good. So, but that's a fair point. I can see that vantage point of that. Maybe what I'll do is I'll take that feedback into consideration, and maybe I'll do that for the second midterm. And then on the final, when we have more time, we're going to have 3 hours. I won't make it too long, but I'll make it longer, but it'll be back to the format of this exam where it's like you sort of have to know when you can apply which equation. So that way it's like, because it's definitely... we're not testing for derivations. There were no derivations on it, though, were there? Right, see? I kept true to my promise, no derivations. It was all problem-solving based and some conceptual stuff as well. I don't think there was anything on there that was beyond the scope of it. And then when it came to the entropy, some of that stuff was a little bit nittier, grittier in the math. I kind of just focused on the conceptual stuff for that reason. I didn't give you anything that was too heavy-duty with, you had to do a bunch of stuff with logs. Yeah, question? Yeah, I could do that. Okay, so that's a good feedback. All right, well, tell you what, we'll just do more pages next time. Does front and back work? Was that okay? Okay. So what we'll do is we'll do front and back, but I'll do more space. So we'll do 3 problems worked out, a full page for each problem in terms of space, and then we'll just do 4 multiple choice and 3 worked problems. That's a promise for the second midterm. But that is going to mean that you're going to have to really know your stuff. Now, I'm not going to. I'll go through. I can tell you right now, there's probably going to be 2 fluid dynamics and 1 simple harmonic motion on the midterm, and then the final is probably going to be like 60%, 60 to 70% new material in the optics range. We'll see how we go as far as the optics goes. We'll start covering the optics before the second midterm, but you won't be expected to do optics on the second midterm. So what I'm going to do with the midterm, the second midterm is I'm going to limit the scope of the material to just 2 chapters, like I did this time. It's just going to be fluid dynamics and simple harmonic motion. There's not going to be any mechanical oscillations or things like that because that takes a lot of time to cover. It's mathematically dense, it's challenging, and it doesn't really add to the physics understanding that much. It's sort of like advanced if you want to go into physics or something, but it's not important for life sciences like the fluids is with blood and everything else, all the applications. Or the optics is important, right? Because we have maybe future optometrists, people who are working in that realm. You're going to learn about the optics of lenses and things like that. That's important too. So we're gonna focus on those things, and I'm cutting out some of the material because historically this course has had to have a pretty large curve because people are covering a lot of material and not in enough depth. I want to comment though, I do want to see more people in office hours. I'm not satisfied with the participation in this class. I saw much better participation last quarter. Maybe it was because it was the morning class, I don't know, but I put everything into this class. So I do way more office hours than the average professor. I do an office hour every time after class. And there's been a lot of times when there's only 1 or 2 people that are in there, which is great for the people who've been coming. But I think that anybody who's not satisfied with their score on this midterm, you have to ask yourself, did I make use of all the office hours? Did I make use of all the discussion sections? Did I make use of everything that was available to me to do well in the course? And if the answer is no, then you know what to do. You're going to have to apply yourself more. This is like a very serious course. I take physics very seriously, but I mean, I expect you to put as much into it as I put into the teaching, right? Because that's why I do extra office hours, because I want to do a better job than average. I want to give you the best learning experience I can, so I maximize the amount of time and investment. But then if I'm in my office hours and only one person comes, that's only a small percentage of the class that's getting help. And everybody could be coming, or at least a lot more people could be coming on any given day, and I could be helping out 10 people. And even better yet, you're all coming to office hours and you're helping out each other, answering each other's questions. That's a useful process too. That's why I get multiple boards going and I have multiple problems worked at once. And then you not only get your questions answered by me, but you also get feedback from other students who've worked the problems, who can relate to you more in that early learning stage, where maybe they can break it down for you in a way that makes sense. So I want to see more participation in office hours, because I want everybody to do well in this class too. I don't want people to be like, oh, I didn't do well on this, it was too hard. It's more like I want it to be like, okay, I put forth a lot of effort, I did everything I could, and I got a good outcome. That's what I want to see. So that's what I will add, that little bit of feedback. I don't think there's been quite enough participation, both in terms of coming to class, because I put a problem on there about work done at constant volume. And we talked about this extensively in class, and I got a lot of questions. I don't see a formula for this on the formula sheet. Where's the formula for work done at constant volume? There is no work done at constant volume, right? There's no displacement. We talked about that a lot. So that's something, that's one of the things, right? You should be doing these problems. You should be paying attention, asking these kinds of questions, thinking about this stuff. It pays to pay attention, right? If we have a constant volume, there's no change in volume, there's no displacement, there's no work done. We talked about that. We talked about that a lot. So yeah, I put that one on there because I wanted to see who was paying attention and not, and who wasn't. Because I guarantee you, everybody who paid attention got that, because there's nobody here who couldn't understand that. Yes? When the second quiz is going to be? So I have a policy where I always announce the quiz at least a week in advance. I would like to make the quizzes just surprise quizzes, because then everybody would show up, and I think the midterm scores would be higher, actually. It would really help you guys out if I could do that. However, CAE has a policy in place where I have to inform the students at least a week in advance. So then the quizzes have to be announced. So I am going to have to announce the quiz a week in advance instead of making it like a pop quiz, which would encourage more attendance. So yeah, it's probably going to be at the end of next week. Okay, now, with that being said, remember, physics is not an easy subject. This material, this subject, is a life devotion for those of us who go into it. It's never easy, right? This is like the kind of material where you jump into this if you like an intellectual challenge, if you like to think. What I want this to be is, I want you to enjoy the material and have fun with it, and not try to be too obsessed with your grade. I know that the system has made it so that all you care about is your grade. I know that. I know that because that's the thing that's wrong with this entire country. Everybody's pitted against each other for one big competition. There's only so many spots for medical school, and you're obsessed with getting that grade, even though the grade isn't necessarily even reflective of what you really learn or anything else, but you're treated as a number, and that sucks. I hate that. I hated that when I was a student, and I honestly reject that personally. What I want you to do is, I want you to view this material as an intellectual journey and try to have fun with it and enjoy the process of learning. And if you don't do amazingly on it, don't see it as a failure. See it as an opportunity to get in there and do better. And also remember, that's why the final, you can improve your score, because if you do better on the final, that's a way to boost up your score. So think of it as like an intellectual journey, an intellectual challenge, and have fun learning the material and learn to like enjoy thinking and just making it a challenge. And that process that just says, if I don't get an A, my life sucks. Just try to like get that out of your system, right? I know that was planted in your brains by computer chip, by the system starting from high school, but like try to like not let that define you completely. Not that getting a good grade doesn't matter, okay? That's why I try to make the material fair, because I don't want people to like work hard and still do lousy. But at the same time, it's like, do it more for the sake of enjoying the learning. Okay, you have a question. Yes. There is a lot of problems. So there's some changes that are going to be made to the course. So the change is this. Now, I'm glad you asked that question because I'm going to address that. So the fluid dynamics takes quite a bit of work and practice. Those problems are assigned for a reason, because I want you to have a lot of practice, invest a lot of time in it. However, we're going to change gears in discussion section. Andrew is going to help you go over those problems in discussions. So you come to discussions and you get support and get help on the homework. There's not going to be any additional problems in discussion that he comes up with or additional worksheets. All the discussions are going to be from now on are going to be concentrated on helping you solve that homework. That's going to stay for the rest of the course. That way you make sure you can do this set of problems and you can know this material. But now you can see why I didn't like give out a bunch of practice exams ahead of time, because the last thing you need is even more material to learn. It's like there's a limit to what you can learn in the amount of time provided. And so by focusing in on these sets of problems and these principles, which are good representatives for the course, that's the key here. So I'm actually working on consolidating time a little bit and making a little bit more targeted focus for the second midterm and the final. So that change is going to take effect from now on. From now on in discussions, you're only going to learn and get help with homework problems. You go to discussion, everybody votes on the problems you think are the hardest, you get help, you set up a study group and you get help during discussions, and hopefully you talk to people that you see eye to eye with or that you learn well with, and you form a little study group so you can study together later on too. That's what I'd like to see. I'd like to see study groups forming where you get support and feedback on solving the problems, and you help support each other's learning. Because that's like an important part of it too, is like there's only so much you're going to learn in the lecture. A lot of it is going to be like getting your hands dirty, solving those problems, thinking it through. I thought I understood it, but I don't quite understand it. What am I missing? What am I missing? You ask other people in the class for help. You figure it out together. You work in it, and then that makes progress and that makes learning happen. So that's another thing that is going to be like a slight change from before. We're going to have more support for the homework problems in discussion. I have no idea what the grades are for the midterm as of yet. So we'll see what happens as far as it goes. But I'm not too concerned. I don't think it's going to be like catastrophic or anything. Yes. Yeah, we can go over the answers. We'll go over the answers to the exam when it gets graded and stuff. Sure, that's not a problem. That can be done pretty easily, like probably like in the next week or so. Yes. I don't know. I don't think that's really going to be necessary. I mean, we'll see, but I doubt that there's going to need to be a curve. I think between when you have you got 2 more exams. You got a second midterm, and you've got another final coming in. Okay, so you've got opportunities to raise your grade. Really, the majority of the course grade hasn't been assigned yet. Okay, and then you've got a certain percentage of points for doing your homework that are automatic. Okay, so you get 100% on the homework for anything that you attempt. It's not graded based off of what your score is at the end. It's based off of how you do all the problems or not, right? You get 100%. The Pearson score that you have is not what you get. You do all the problems, you get 100%. That's gonna help out a lot. I think with those things doing that way properly, I don't really think it's gonna be necessary to do much of a curve. Okay, there is one kind of a little bit of a curve that is gonna be put into place. So for the first problem where there was that typo when I said Kelvin and I meant Celsius, so I'm actually gonna give everybody the full points for that part A. So you'll get 10 points automatically for that one, because I do think that it's only fair to give points. If there's a typo and the CAE didn't see the typo, they might not know what to do, and I don't think it's fair to demand perfection on a problem where there was a small typo. So even though I made the announcement to everybody at the beginning to change it over, I did decide, like, I am gonna award full points for that part A of that problem, okay? So that's 10 points there. So that you could think of that as like a letter grade curve, de facto, so to speak. But that's, yeah, you know, that's only fair. I think if it's a typo or something, it's like, I'm not gonna like hold you responsible for something like that. Like that's only fair, yeah. So I figured you'd be pretty happy to hear about that. But I do think it's fair. Like I'm not, I have no problem with that. That's just, yes. Yeah, they're not due until finals. Yes, you should be doing them now. Right now, you should be plugged in. This is a quarter system. I don't like doing physics on the quarter system, but that's what we're left with. It's fast-paced. It's heavy-hitting. Get to work on these problems. Right, exactly. So, and then we're going to go over some more derivations today, okay? Because we have more things to talk to, and I don't know what's going on with this, why this isn't working. Let's see. HDMI. Okay, why isn't this working? Here we go. Okay. There are. Okay, so there's going to be a homework set for simple harmonic motion after the fluids, and then there's going to be maybe there's going to be like 2 more homeworks total. I think after the simple harmonic. Let's see. This is week 6, right? Okay, so week 6. Okay, you're going to need at least to the end of this week and most of next week to do. All right, let's just do 2 more homeworks after this one. We're going to do fluids, we're going to do simple harmonic motion, and then we're going to do an optics homework, and that's it. We'll be done, okay? That's enough. That's fair. But there'll be big homeworks, but it'll be like, that's it. Yes? There may be, yeah. We'll probably do an extra credit opportunity for a survey or something like that at the end of the class. You do the survey, you get an extra credit for doing the survey or something. Yeah, we'll do some extra credit. I'm sure there'll be a few things that come up here and there. Yes? Yes. Yes. Well, I'd say by the time the next midterm comes around, know how to do all of that homework and the simple harmonic motion homework. And then when the final comes around, know how to do that homework, the simple harmonic motion, and the optics homework. And that's enough. Okay, so we've got, 5 weeks left, and we're going to have a total of 3 homeworks. One of them's already been assigned. So there's only going to be 2 more homeworks. I'm not going to assign them just yet because I want to see about covering diffraction, adding diffraction to the optics, geometric optics topic, because you have a lab on diffraction. I want to cover that. I didn't have time to cover it last time. Yeah. Final's going to be cumulative, but it's going to be more new material than, just as much new material as cumulative material. Okay? So it's going to be like 50% cumulative, where it's like stuff that we've talked about from the other material, and 50% optics. Maybe a little more than 50% optics, where optics is not going to be on the second midterm. Optics is just going to be on the final. Okay? That's what I did last time too, and it worked out pretty well for people as far as making the content manageable. But yeah, it's not an easy class, but I think it's structured in such a way that if you really plug in, come to office hours, stay focused, works out. It's a fair class. Definitely fair. Anybody have any questions or comments about this? You're totally welcome to give me your feedback. I already took feedback into account. We're going to think about putting equations on a few of the problems for sake of time. Maybe not everything, but for sake of time, a few of them. And then we're going to think about, we're going to talk about like doing fewer problems. So we're going to do 3 worked problems for the second midterm. And so it's going to be 7 problems instead of 8. And more space to work out the problem. So each problem will have its own page. So we'll have 3 pages scanned instead of just like 2. Maybe, yeah. Okay. And then any more questions before we get started? Or comments about this? You're totally welcome to ask. Okay, good. So now we're going to talk about the equation of continuity. Continuity is a very important concept in physics. In fact, it's sort of one of the most fundamental guiding principles we have. And continuity can apply to virtually any system at all that's undergoing some kind of process, transport process. By transport, I mean things are moving from one place to the next. We have these equations of continuity for all kinds of systems. Fluids obey it. You could think of it as like, okay, I have a continuity equation. That means that fluid that travels from this spot has to go and be conserved as it travels to another spot. And various things could change as the fluid is in transport. Maybe the cross-sectional area of a pipe changes. Maybe the fluid has to flow down some region or something, some hill. Some potential energy might change for the fluid. But it obeys the equation of continuity. It's a very fundamental thing. You aren't expected to derive this because it's a little bit of differential equations. However, just know how to apply it. Applying it is simply a matter of applied math and a little bit of algebra. Okay, so we have a fluid flowing through a tube, oil through a pipe, or blood through an artery. If the tube's diameter changes, what happens to the speed of the fluid? Okay, so here we can see we have this region of fluid flowing, and there's 2 different cross-sectional areas and 2 different volumes in that cross-sectional area. The flow speed, the velocity, changes as this fluid flow occurs. And why does it change? Well, these 2 cylinders of fluid have the same volume. These 2 volumes are the same. This volume is the same as this volume. So delta V2 equals delta V1. But look at this. Neither A1 nor A2 they're not equal, and delta X is not equal, delta X1 is not equal to delta X2. As you can see here, this delta X covers a larger delta X than it does here, even as this causes a larger area. So we have a different distance that's followed in the same volume of fluid flow. So we have to figure out, okay, how do we relate this? Well, the equation of continuity relating the speed V of an incompressible fluid to the cross-sectional area A of the tube in which it flows is given by this. V1 A1 equals V2 A2. So V1 A1 equals V2 A2. That's the equation of continuity. We assume the fluid flow is steady, there's no turbulence, that's laminar flow, and an equal volume of fluid must leave the tube as entering it. It's sort of a conservation equation, a conservation of fluid parcel equation. The number of particles per unit time of fluid entering one region must equal that of the other region, even as the width of the tubes changes. So what's going to happen is, as my width of my tube or my cross-sectional area, because those are the same things, as that changes, the speed of my fluid is going to change in those regions. And the two speeds are related by the ratio of the areas, the cross-sectional areas. Because I can divide this, A1, and then V1 is just simply equal to V2 times A2 to over A1. So depending upon whether A2 or A1 is bigger, whichever one is bigger, that's going to determine whether V1 is faster or V2 is faster. Okay? So you can play around with those numbers. So let's say I have A1 is equal to 4 times A2. That means that A2 is only a fourth what A1 is. Let's see what happens in that case. Let's play around with this equation and see what happens to the velocity. So what does this do to the velocity? What's this do to the velocity of the fluid? So let's plug that in. So we've got V1, A1 is 4 A2. That's going to be equal to V2 A2. And then we can just divide by A2, both sides by A2, and then V2 is equal to 4 V1. Okay? So that's what happens when we have a change in area going in that direction. Now, what if we reverse it? What if A1 is equal to what? We're going to have A1 is equal to 1/4 A2. So 4 A1 equals A2. Okay? So what happens then? We go back to this equation and we have V1 and then A1 equals V2 4 A1. Okay? Let's divide by A1. Okay, V1 is equal to 4 times V2. Okay. So then we have the opposite case. Okay? Anybody confused about that? Yes. Yeah, sure, no problem. Sure, no problem. And then I'm not sure why this projector is not working, but that's like unacceptable that it keeps not working. That really gets on my nerves. Sorry. Okay. Yeah, okay, so what are we saying here? Let's draw a picture. You're asking for a picture is what you're asking for. So you say, okay, how do I visualize this? Okay, let's take the first case. A1 is equal to 4 times A2. So here we go. A1 is like this, and then A2 is like, so we have R, right? Pi R squared is going to be A, pi R squared. So pi R1 squared, so pi R1 squared is equal to what? That's A1, and that's equal to 1/4 pi R2 squared. So then we have an equation that relates R1 to R2, okay? So you could solve and say, I could say, what's this radius of this smaller region? And you could solve for it. So what that says is the fluid parcel flows at a certain speed as it goes through this cross-sectional area. Then what happens when the cross-sectional area is only 1/4? This is A2. Pretend this is like exactly 1/4 of that. It looks even like a little smaller, but just pretend it's 1/4. Okay? So what happens to V2 in that limit? Okay? So V2 is 4V1, right? Okay? So it depends on the situation. So let's see. So we've got A1 is 4 times A2. So we have V1 A1 is equal to V2 A2. And then we have A1 is 4A2. Okay? So we have 4A2. Then we can cancel out our A's, and then we have V2 is equal to 4 times V1. So that tells you what happens to the velocity in that case. It's going faster, right? So that makes sense, right? Because in order for there to be an equal amount of volume, it has to be going a lot faster in order for these volumes to be equal, because it has to cover more distance in the same amount of time to flow through to have the conservation equation obeyed. Is that good? Okay, cool. Everybody like that derivation? Yeah? Okay. So, an important consequence of the continuity is that flow is faster in narrower parts of a tube, slower in wider parts. There you go. So now we've seen in words what we already saw there pictorially. You're familiar with this conclusion from many everyday observations. Okay, that makes sense. So we can go through that. Okay, now we can talk a little bit more detail about the rate at which fluid flows through the tube. It's volume per second. Okay, this is called the volume flow rate. So before we talked about flow through a cross-sectional area. Now if we multiply that change in volume, or if we multiply that velocity, let's multiply this velocity times an area here. And this V, the velocity at which it flows, times an area, gives us a volume flow rate, Q. And that's equal to delta V delta T, the amount of volume covered per unit time. And you can see that simply by it's going this many meters per second. So this meters per second, this distance of meters per second times my area is a volume. It's a cylinder. And so is this. This is also a cylinder. And these two volumes have to be equal. But then in order for that to be the case, this cylinder has to be wider along this dimension than it is here. Okay? That's the volume conservation of volume flow rate. We say that the Q1 equals Q2. Okay? Okay, so now we can apply this to the physics of breathing. This is pretty cool. We've got this adult who breathes 12 times per minute and inhales a total of 8 liters of air. The breathing cycle is not symmetrical. 40% of the time is spent in inhalation and 60% in exhalation. The average diameter of an adult male's trachea, the windpipe, is 1.8 centimeters. The trachea branches into 2 bronchia as it descends into the lungs. What's the average airspeed in the trachea during a resting inhalation, and what diameter bronchi will maintain this airspeed? Okay, what's the application to this? If I want to measure my congestion, I have a patient who's suffering from pneumonia. I can measure their amount of congestion by comparing it to a healthy adult. But how do I know what a healthy adult's lungs are? This is it. This is what we use. Doctors use these numbers that they can calculate, and others, but this is one of them, to figure out. So what's going to happen in somebody's lungs that are congested and also their trachea? Their volume flow rate is going to change because their cross-sectional area is going to be a lot smaller, isn't it? Whereas another way that this could apply to blood clots, okay? What's going to happen to an artery as it gets clogged with plaque? We're going to have this plaque comes in and it's going to reduce the flow rate. There's going to be a region where this is mostly not coated in plaque, and then it comes to a region where it is. So we're going to have V1 and V2, and you can see here there's going to be a big discrepancy there. So that's why this is so important to medicine. It's very important to medicine, and so you need to think about these ideas and train your mind to think about things mechanically and in terms of problem solving. Don't just try to memorize numbers and just try to like memorize symptoms. Like a lot of doctors are not good at diagnosing their patients because they try to do that. Be a problem solver, okay? As a doctor, you won't be expected to necessarily discover new things, but you have to take a look at a collection of symptoms and take measurements and look at facts and use problem-solving skills, some of which is put to good use in this type of problem. So let's figure this out. Okay, so we've got 12 breaths per minute for a healthy patient. One cycle takes 5 seconds. 40% of that, or 2 seconds, is the time for one inhalation. So what we want to do is we want to relate that information to the air volume of one inhalation. Now notice something interesting about this problem, okay? We're not talking about blood or fluid, are we? But we are, because air counts as a fluid. So even though we think of air as a gas, and it is, both gases and liquids obey these equations. So anything that works for a liquid like water, it also works for gases in this class too. Both of these are fluids. So that's why we can immediately jump from blood to air in the lungs, because they're both fluids. Okay, so we're going to use this volume flow rate equation to solve this problem. So what I want you to do is maybe pull out a piece of paper and sort of write this out and try to think about how we do this, because it's a good problem to derive. Okay, so the volume flow rate is delta V over delta T. That's Q. So we've got the volume per unit time. And we know what the unit of time is, 12 breaths per minute. So delta T is going to be, one cycle is 5 seconds. And 40% of that, 2 seconds, is the time for one inhalation. So we have 60 seconds divided by 12 breaths, right? And that gives us 5 seconds. But then they tell us in the beginning of the problem that 40% of that is spent on inhalation. So we multiply that by 40 and 40%, and we get 2 seconds for one inhalation. So that tells us part of our delta T in our flow rate equation. And then the other thing is, we know that the air volume of one inhalation is 8 liters divided by 12. We were given that in the beginning of the problem too, 0.67 liters. So that gives us our other side of our equation. Okay, and then we had 2 seconds here. So we have 0.67 liters divided by 2 seconds. And then we have this conversion factor. 1 meters cubed is 1,000 liters. Okay? I wouldn't expect you to memorize that. I do expect you to be able to convert from centimeters cubed to meters cubed, because we did that in class. And if you have any questions about that, somebody asked me about that in the midterm. If you have any questions, you're welcome to come to office hours, and I'll show you that derivation 1,000 times. Okay? It's just basically converting from centimeters to meters 3 times, because you have 3 powers of it. But for this conversion factor, I wouldn't expect you to memorize that. Okay, so we can convert that, though, into meters cubed per liter, and then we get, so we have this times 1 over 1,000. Just erase that then. And then we're going to get 3.3 times 10 to the minus 4, because this is a really big number. And what are the units of that? Meters cubed per second. So that's the amount of volume that your inhalation is covering. That's amazing. We can actually figure out how much volume of air a healthy person can breathe in. So you could calculate how long somebody could run out of oxygen in a room pretty accurately from that, couldn't you? You would just take the volume of air in the room and assume that it's a sealed room, and a perfectly sealed room, and then you could just figure out, okay, how long does it take until that whole room is covered? As you can see, that's a really small amount of meters. So even if you place a person in like a room, how many meters cubed is the average room? I don't know. 10 meters by 10 meters, top by 10 meters, that's a lot of meters cubed. It's going to take like days for you to run out of oxygen. But you could calculate that just from that. You could figure out how long it takes the oxygen to run out, essentially. Of course, the air you breathe in is not pure oxygen, it's a mixture. So you'd have to include that into your factor, like, okay, you need this much oxygen for this much air, but how long would it take it to all turn into CO2, where you run out of oxygen in the process? Okay, so the flow rate through a cross-sectional area is Q is V times A, pi r squared times V. All right, so let's think about that for a second. They just kind of give that, but I want to sort of derive that a little bit better. So I'm not going to erase this because we could think of this as the model for a person's throat. So just kind of pretend that the person is laying on their side here, and they've got arms, and then they've got like a head, and then that's their throat. Okay, same idea. Okay, so we can totally extend that to a person. Put some hair on them, whatever. Okay, that's good enough. Okay, so the flow rate through the cross-sectional area is Q. That's V times A. Okay, same idea as here, and then the pi r squared V is the area. So pi r squared V. This is just the area of the person's trachea. So this is R, the radius of their trachea here. That's where they're coming up with that for. Okay? That's the radius of their trachea. And then we have our flow rate from before, 3.3 times 10 to the minus 4. We came up with that up there for the flow rate. So then we have the volume then is Q over the area. Okay? And then, so it's going to be 3.3 times 10 to the minus 4 meters cubed per second divided by the area, pi r squared. Okay, and then for the radius of the trachea, they gave that to us at the beginning of the problem as well in terms of like centimeters. So it's 0.009, okay, so 0.009 squared, pi r squared. And then that gives us a flow rate, all those are numbers, of 1.3 meters per second. And then what's going to happen to somebody who's super congested? What's going to happen to their flow rate? It's going to be different, right? And that's a problem because in order to have the oxygen diffusion process occur, you have to have a nice, smooth transition where the gas has the right amount of time to settle in. It can't come in too fast or too slow. And that's something that they learned the hard way. When they first put people on ventilators, when they had the COVID thing, right? If the flow rate isn't right, the patient's going to die because you give them the oxygen, but you push it in too fast, and their body can't absorb the gas properly enough. They also, that's assuming that they can still even have any oxygen transport, that their alveoli and stuff are still functioning. If it gets bad enough, then they can't even do that, and you have to put them on ECMO. But assuming that they still have that, you can put them on a ventilator, but you have to get that flow speed correct. You have to dial that in. You see how mechanical this is? It's very mechanical. And a knowledge of physics really comes into play when we're dealing with like medicine at all levels. And so that's an example of how it's important. So now we know what the flow rate should be for a healthy patient if they need their oxygen to be delivered to them because they don't have any strength. Maybe they have essentially no way to breathe in oxygen if they're paralyzed or something momentarily, and we have them sedated, and we have to do surgery, and we have an oxygen tube. Now we know how fast we need to hook that oxygen up to them. Dial that in for the hospital. Okay, so then the continuity requires that it's going to be 1.3 meters per second. The continuity requires the air to flow through the bronchia at the same total rate, but there are 2 bronchia, and thus we have 2 times this speed, and then we have this equation all over again, which we can calculate. So then there's no loss of airspeed as the air moves from the trachea to the bronchia, and so then the V bronchia is equal to the V trachea, and thus the radius of the bronchia is the radius of the trachea divided by square root of 2. So the bronchia diameter will be twice of this because the radius is half the diameter. So we also can figure out what the radius is going to be as this thing spreads out and goes directed into the lungs of the patient. Because it has to be, basically this branches off into 2 different tubes, and each one goes into their separate lung. The lungs are like inflatable, like sponge-like material. Okay? Let's see, how are we doing for time? Okay, good. All right, so that's how we solve that problem. Okay, anybody have any questions about this problem? No questions about this problem. Yes? Yes. So the question is, can I explain the difference between volume flow rate and flow speed? Yes, I can. So here's what it is. The flow speed is essentially the speed of every particle in my fluid at a given moment. So I've got a little particle of fluid, maybe a gas, a parcel of gas or a parcel of fluid. And the idea here is it's traveling in some region here, and it's traveling at this instantaneous moment. That's the flow speed or the flow velocity. The volume flow rate is just the amount of volume that I get per unit time. So what I do is I multiply the volume flow rate by the distance, and that tells me my volume flow rate, because it's going to be Q times V, essentially. Or it's going to be, A times V. That's going to be my Q, because I have a certain volume of velocity in meters per second times an area in meters squared. And what does that get me? Units of meters cubed per second, which is precisely the units of volume flow rate. It's the amount of, so the faster the velocity is going, the more distance in this direction I'm going to cover per unit time. So the volume flow rate for this region is the same as this region. These 2 volumes are the same, but as you can see here, this velocity has to be a lot greater than V1 in order for me to cover this much more volume and make this volume equal to this volume. Yes? Yes, for this process, yes. The volume flow rate stays constant. That's a continuity equation. It's a constant flow rate. And so in order for the flow rate to stay constant, I have to have the velocity changes depending upon how my cross-sectional area changes in response to that. Okay, great question. All right, so does everybody understand these principles now for this? Okay, maybe you think you do. Go home and try the problems and work the problems, and then you will. That last process is important. Okay, and then we're not going to do any more today. Tomorrow we'll talk, or Wednesday we'll talk about Bernoulli's equation. It's a very cool equation. Okay, have a great one.